Okay, hi everyone. So we've been working with exponentials and solving for exponentials using continuous and using compound interest. Now let's just go back and talk about just basic exponential growth and when do we need these special formulas and when we don't. So let me give you an example. If I told you my bank account doubles every 5 years. Okay, so you're gonna double every 5 years. And if I start with a bank account principal of, let's say, $100, how much will I have? What would that account be after 25 years? Okay, so what would happen after 25 years? Well, if we're doubling, are you okay with doubling? So we can write it down as my first year. Here's my initial, right? Here's our years. And this is how much money we have. So let's just create a table. Nothing super fancy. So at 0 years, we have $100. At 5 years later, we have 200 because we're doubling. At 10 years, we have 400. At 15 years, we have 800. At 20 years, we have 1600. And at 25 years, we have 3200. And great, that works, right? But is there a faster way for us to do this? A faster way for us to do this? Now, we just say we double. So we took 100, right? And to get to this here, we just times 2. So we took 100 and then we times 2. And then on our next year, we took our 100 times 2 and then we multiplied this by 2. Right? That's how we got 400. And then to get to our next year, we took this answer 100 times 2 and then we multiplied by 2 again to get 800. Anyone seeing a pattern here? What am I doing at every step? I'm just multiplying by what? I'm just multiplying by 2. Hopefully you can see that. So what's a fast way for me to, instead of writing 2 times 2 times 2 times 2, right? We can use exponents. And this takes us back to compound interest. We're taking our previous amount and then we're multiplying it by the same multiple to get our new value. So instead of writing it in this way, we could say it's 100, which is our principal, times 2 to the t power. Because it's 2 times 2, that's 2 to the 1, right? Then 2 times 2 is 2 squared, and then 2 times 2 times 2 is 2 cubed, and then 2 times 2 times 2 times 2 to the fourth. So we can come up with an equation here where we can say, hey, I can tell you how much you have on this idea of doubling, right? Because we're doubling is just multiplying by 2. And we take it to this t power. How many times do you want to count it? Now, have we seen this equation before? Actually, kinda. Because we can write this as a compound interest problem, a simple one. If we say A is equal to our starting principal plus 100% plus how much do we add in interest? We're going to double, aren't we? We're going to double. And the number of years, well, in this case, we don't double every year, we double every 5 years. And in this case, our t value is actually the number of times. Number of times. In this case, to get from 0 years to 25 years, well, how many steps was that? There's actually one more step, and that's going to be 2 to the 5th. So we would say it didn't take 25 years, 25 iterations. It took only 5 iterations, because for one iteration to happen, it took 5 years to get there. What I mean is we say 25 divided by 5, and that's our number. This is the number of times we double. Okay. Now, we could change this to a different way of looking at it. But I feel like sometimes we say this, you'll double in 5 years. Great. But how much do I make per year? I don't care. It's easier for me to think about me doubling every 5 years. Could we have come up with this as a rate per year? Yeah, we could come up with this as a rate per year. And we could have created that as our new R value. But wasn't the R value so much easier to say this is like we double by 100% every 5 years? So now this is, again, another way of looking at this type of problem, this compound interest problem. Now let's do the same problem now. So I'm going to ask you, how much would I have after 50 years? Okay, so if we start off with $100 and we double again every 5 years, okay, how much would I have after 50 years? Now, since we're doubling is pretty easy. We said we're just going to multiply by 2 every single time. Now, to get from 0 years and counting by 5s, how can I count by 5s? How many 5s do we have to get all the way up to 50? Well, if we have 50 years, darn it, and we're 15. If we have 50 years, and we say if I divide it by 5, we're going to have 10 iterations. So we're going to go through this repeating cycle every 5 years. How many times are we going to do it? We're going to do it 10 times total. So in this problem here, we can say we have 100 times 2 to the what exponent? How many times are we going to multiply this by 2? How many times are we going to double this? We're going to double this 10 times. Now this is going to be a lot of money. This is kind of a lot. So on your calculators, you guys can try practicing this right now. I always like typing the exponent first because that's always the most difficult part. So I'll say 2xy 10. That's going to be a huge number. That's going to be 100 times 1024. And this gives us 102400. So we went from $100, and if I could double my value every 5 years, in 50 years when I retire, I'm going to have about $100,000 just from that initial investment of $100. I'm going to have to hustle a lot to get that to double every 5 years. That's a lot of hustling, but you can see where this growth happens. Sure, I'm going to show you guys in the calculator. I'm going to get my calculator. Oops, that logged me out. Shoot. Okay, here's how I do it in the calculator. Oops. I first hit 2, then we have an exponent button. If you can see right here, it says xy, and then I'm gonna hit 10, and that's gonna give me 2 to the 10th power. So I usually try to do the exponents first, and then I'm gonna multiply this by the 100. And then we end up with $102,000 and $102,400. 1,002, 102,400. Darn it, man. Sorry, my brain's a little glitchy. I'm doing attendance real quick at the same time. Okay. Now, I think this is kind of cool. We can talk about bacteria doing the same thing. We can say if you start with, let's say 10 cells of bacteria, let's say 10 bacteria. Oops. And let's say bacteria E. coli, they say doubles, right? You end up with 1 cell, and then it splits up into 2 cells, and then these 2 split up into 2 more cells. Okay, and these cells all split up into 2, and you guys get the idea. That's why bacteria grow so quickly, right? They take 1 and then they split into 2, right? Okay. As we have start with 10 bacteria, we're just touching something, and bacteria splits every 20 minutes. Okay, that's the time it takes bacteria to separate. Now, how much bacteria would I have after not an hour, but after 24 hours? I just kind of jumped there. So after 24 hours, how much bacteria would we have? And this is why bacteria gets kind of dangerous, even if you have a little bit. So we'll see. So we have to discuss, well, what's going on with our numbers? Well, we start with 10, and we're gonna double this, right? Double it, and double it, and double it, and double it and double it. We're going to double this a bunch of times. But how many times are we going to double it? So let's talk about how many times does 20 minutes go into 24 hours? And that's the biggest conversion we have to figure out. How many times am I going to double it? Well, in 1 hour, would you be okay to say, at least let's look at examples. In 1 hour, how many 20 minutes are in 1 hour? Wouldn't you say there are 3 20 minutes? There are 3 20 minutes in 1 hour. Okay. And then how many hours are in 24 hours? Well, there are 24 hours, right? So in 24 hours, there are 24 hours. So there's 24 of 3. So in 24 hours, we have 60, 72 times we're going to split. Are you guys okay with me coming up with those numbers? So in 24 hours, we're not going to split 24 times because every hour has 3 splits in it, because every split, it takes about 20 minutes to split. So what we do is we're trying to figure out how many times does my interval happen in my total time period given. Fine, so if we start with 10, and do I want to actually multiply by 2 times 2 times 2 times 2? And we're going to do this iteration 72 times? No. So what happens, we're going to write 10 to the 2 times 2 to the 72. $72 times. Sorry, I have people coming in right now. Class late. Now this is going to be a huge number. And this is why bacteria can get kind of scary and nasty pretty quickly. So let's do 72. Oh, wrong one, not 72. We need the base first, which is 2xy 72 equals, that's a huge number there, right? We can't even write it. And then times this by 10. Forget it. It's just like, it's 4.7 times 10 to the 22 exponent. That's 22 decimal places. That's huge, right? So that's why we're afraid of bacteria. So this way for us to talk about compounding values, exponential growth, it's because these don't grow as like a linear line. These actually end up shooting up very quickly. And this model is 2 to the x, you can say. This 10 times 2 to the x. So after 72 spaces, 72, this is to the moon. Okay. If we want to do something reasonable, that's what happens after 4 hours. Let's try that. If I start with 10 bacteria, and our time is going to be 4 hours. And again, this bacteria splits every 20 minutes. How many 20 minutes are in 4 hours? Okay, in the first hour, it's 3 times. In the second hour, it's 6 times. In the third hour, it's 9 times. In the fourth hour, it's 12 times. But you could also say how many 20 minutes are in 1 hour? It's 3. So 3 times 12 is, no, 3 times 4, I'm sorry. I said the answer. 3 times 4 is 12. Okay, so we're gonna do the split 12 times. 10 times 2 to the 12th power. 2 to the 12th power times 100, or times 10. From 10, we went into 40,960 bacteria. Okay, let's look at a half-life problem. What half-life is atoms, let's say decay. So let's say you have a bunch of atoms, right? And then if they're not stable, they start to actually fall apart. And as they fall apart, you end up having less of it. And this idea of half-life is how long does it take for half the amount of atoms to be left over? Okay. You can think of it as allowance. If I give you $100, how long will it take you to then have only half the amount left? Maybe a week, maybe 2 weeks. And then how much longer will it take you to have half of that? So we're reducing by half every single time. So that's what the half-life model. They say half-life meaning how long does it take to end up with half? Not the half of the life of it. It's how much do we end up with half. So if we talk about this radioactive tungsten, some tungsten, will be left after 2 days if the half-life is 1 day, and you start off with 664 grams. So if we start off with this, 664, after 1 day, the half-life means we end up with half of it. So that's 332 grams. And after the next day, we have half of that. So half of this is 15, 16, 166 grams. Okay. So whenever you have half-life, the meaning of half-life is that you have half as much. Now, how would we write this as exponential model for us? We start off with 664. And what am I multiplying every single time after every iteration? I'm multiplying by half. Right? And then after the next day, I'm going to take this answer and multiply this by half. So at every iteration, I'm halving it. It's a nice whole half. So it's really 664, 1/2 to the t power. And the t is the number of iterations we want to do. Okay, so this model is very similar to our doubling, except instead of doubling, we're halving it. Could we triple something? Yeah. This would become a 3 then instead. The idea is, what am I multiplying repeatedly over and over and over? That's what we're going to take the exponent of. And that's the idea of exponents. We're able to multiply things quickly with exponents. So our answer is 166. 166. Yeah, easy, right? This one's doubling our populations. We talked about this before. These are pretty easy problems. Now, what happens if it doesn't fit nicely? In this case, this is still going to fit nicely. A lot of these problems are going to fit nicely. So how do we get from 90 here? Let's do this one, might as well. This is an easy one again. What happens when we get 90 to 54? So the problem says a city has a population of 168,100 doubles in every 90 years. What's the population after 540 years? Well, how many times are we going to double? Well, to get from 90 to 540, it's just 540 divided by 90. That gives us how many? That's going to be 9 times 6 is 54. 6 times. So this population will double 6 times over to get from our current population of 168,000 to 540 years. Great. Okay, so 540 years. Here we go. So 500. So we have 168, comma 1, 2, 3. Oh, sorry, I misread that one. 100. I should make it look nicer. This is my population, and we said we're going to double, right? How many times are we going to double it? We're going to double it 6 times. We're not going to double it 540 times because it doesn't double every year. It doubles every 90 years. So how many 90 years is it going to take me to get to 540? It's going to take us 6 iterations. So let's go ahead and write this on my calculator. Oops. Whatever. We have the number. Okay, we're going to take 2xy. We said it's going to happen 6 times. And then we'll multiply this by 168, 100. And that gives us the population expected after 500 years is going to be over 10 million. Now, here is a slightly different type of problem, except we're not going to double it anymore. The rabbit population in Fullerton County, which has like, oh my gosh, there's 2,000 rabbits there, is increased by 15% every year. So if it's 15%, that's not doubling. And so we go back to our easy compound interest equation. So if we start off, A is equal to P, 1 plus R to the T. We're going to increase our population. Our rate is at 15%, which is 0.15. We want to figure out how many rabbits will be there after 2 years. with an initial population of 2000. A is equal to 2100, 2010, 1 plus 0.15 to the number of years, 2. And the reason why we can write 2 here is because this rate that they gave us is per year. So how many years? We're going to hit 15 times. We're going to do 15% twice. You can actually do it manually, 1.15, and then multiply this answer again by 1.15, which is the same thing as doing it with our equation. Okay. All right. What if this was a population of bunnies, but it was diseased, and the population was decreasing by 15% every year? How would that change this problem? Instead of writing increase, what if I wrote instead decrease? The problem would still be very similar, except instead of adding, instead of adding 1, I'm going to minus 5.15 because it's decreasing. So that's the main difference, the two. That's the main difference in the two. So if we end up with a problem that ends up decreasing, that'll probably be one of these problems coming up. It's increasing. I saw some of these problems that were decreasing. So if you do see a decreasing problem, you're going to minus. Okay, that's it. All right.